Hello everyone. So in the last video, we defined what it means for a function to be continuous, and we said that it was something useful to be interested in. For instance, continuous functions are those where we can find the limits by substitution. And also there are going to be some other results later that require the function to be continuous that we're going to be interested in. So if we want to have, as many points of continuity and as many continuous functions as possible, we need to do a little bit of work. So that's what we're going to do in this video. We're going to try to find as many points as possible where functions are continuous and try to build up our category of continuous functions. Okay, so let's get started. So what does it mean for a function to be continuous at more than one point? Well, it just means that it's continuous at all of those points separately. So a function is going to be continuous on an interval if it's continuous at every number in that interval. And here, so this is clear, for instance, what I mean if I have an open interval. But what about if you have a closed interval, say a closed interval 0, 1? Okay, then I can't approach 0 from both sides, right? I can only approach 0 from the right if I'm in the closed interval 0, 1. So if there are, those endpoints of an interval, then we mean continuity from one side. Okay, so continuity at endpoints means continuous from the left or continuous on the right. We can only approach the point from inside the domain. Okay, so let's see an example where we prove that a function is continuous on an interval. So here's our function. Let's say f of x is 1 minus the square root of 1 minus x squared. And it has domain closed interval -1 to +1, right? Because we have a square root, we want to make sure the inside of the square root is positive, so we have to restrict to -1, 1 closed interval. And let's try to prove that this function is continuous on the interval from -1 to 1 with closed endpoints. Okay, so if we want to show it's continuous inside that interval, then we have to show that it's continuous at every number in that interval. So rather than pick a particular number like 0 or 1 or a half or something like that, which would only show a continuity at one point, let's take a, which is just any number in -1, 1, and try to check that it's continuous at a. So what does that mean? It means that we have to figure out what is the limit as x tends to a. So we have to compute the limit as x tends to a, and we have to then check that is equal to f of a. Okay, so let's try to do that. So let's take the limit as x tends to a. And if a is -1 or if a is +1, everything is going to be a one-sided limit so that it makes sense, right? Because I cannot approach -1 from the left, I can only approach it from the right. And I cannot approach 1 from the right, I can only approach it from the left. Okay, so here are a couple of steps. So firstly, I'm claiming that 1 minus x squared tends to 1 minus a squared. So why is that true? Well, 1 minus x squared, forgetting about everything else where it came from, 1 minus x squared is just a polynomial. And we said that polynomials, those are continuous, those ones we can find the limit just by plugging in, right? That was an application of the limit laws. So 1 minus x tends to 1 minus a squared. And then I just want to emphasize here that since a is strictly between, or is in the closed interval -1, 1, 1 minus a squared is non-negative. Okay, and then we had another limit law that said if the limit was positive, then we can take roots of both sides, right? So if 1 minus x squared tends to 1 minus a squared, then the square root of 1 minus x squared will tend to the square root of 1 minus a squared. And then finally, we're using the difference rule. So 1 tends to 1. Square root of 1 minus x squared, we just said tends to the square root of 1 minus a squared. So 1 minus the square root of 1 minus x squared will tend to 1 minus the square root of 1 minus a squared. So we use direct substitution for polynomials for the first step. Then we use the rule with roots. And then we use the difference rule for limits. Okay. So we managed to compute the limit of f of x as x tends to a. It's 1 minus the square root of 1 minus a squared. And then, okay, we're supposed to check that's f of a, but that is f of a, right? If we just substitute directly, f of a is 1 minus the square root of 1 minus a squared. Okay, so we've managed to show that f of x tends to f of a. So which means that f is continuous at a. Since a was arbitrary, that tells us that f is continuous on the whole interval -1 to 1. Okay, so here is the same example in a picture. So here's the graph of y equals 1 minus the square root of 1 minus x squared. From -1 to 1, it's not defined outside of that. And let's say we want to take some number a that I didn't mark on the graph, but let's say here is a where the mouse cursor is. The function is nicely smooth, it's nicely joined, there are no jumps. If we try to take the limit as x tends to a, it's going to approach the function value at a. So this is a very nice curve. Okay, so here we managed to show that one function was continuous. But if we had to do that, manually for every function that we want to show continuous, it will get a little tedious after a while and very complicated. So as quite often in calculus and mathematics in general, you want to understand a couple of building blocks and then build everything up from those building blocks using rules that combine them. So here are going to be some rules that can combine them. And they sound obvious, but if we keep applying these rules, then just like with limits, we can handle way more complicated cases. So let's suppose we have two functions f and g, which are continuous at a, and c is a constant. Then just based on that, we can say the following functions are continuous at a. So f plus g. So if f and g are continuous at a, then f plus g is continuous at a. So I'm not going to explain all of these steps why they're true, but let me just explain this one. What does it mean for f plus g to be continuous? It would mean that the limit of f plus g as x tends to a is the value of f plus g at a. Okay, the limit of f plus g by the sum rule for limits, that's the limit of f plus the limit of g. Okay, we know that f and g are continuous. So the limit of f is f of a, the limit of g is g of a. So the limit of f plus the limit of g becomes f of a plus g of a, which is our function value at a, right? F plus g of a. Okay, not a big deal if you didn't follow that, but hopefully you'll believe me that this is a straightforward consequence of the rule we already have for finding limits of sums. Okay. Same thing with f minus g with the same argument. So f minus g will be continuous. A constant times f will be continuous. The product f times g will be continuous. And f divided by g will also be continuous provided g of a is not equal to 0. So provided the bottom is not 0. So in general, in calculus, if you see the bottom 0, that's bad news. So you don't want to deal with that. You don't want to have that. It doesn't make sense. So the quotient will be continuous provided g of a is not 0. Okay, so where are we going? So here if we start with two continuous functions, then we can build up some more continuous functions. And that sounds great, but right now we have the problem of we don't have many continuous functions to start with. So if we want to build more from functions we already know, we should have some functions that we already know that are continuous. So here are going to be some functions that we know are continuous. And here I wrote every point in the domain. So these functions are going to have different domains. So we have to make sure we're in the domain for the function to make sense, right? So starting off, polynomials. So polynomials, the domain is the entire real line. They're continuous everywhere. Rational functions, remember those are one polynomial divided by another. And the domain of those is whenever the bottom is non-zero. So they're continuous whenever the bottom is non-zero. And then root functions, so for instance, square root x, cube root x, things involving those expressions, those are continuous. And then trigonometric functions and inverse trigonometric functions are continuous everywhere in the domain. For instance, sine and cosine are continuous everywhere. Tangent is continuous when the bottom is non-zero, so when it's defined, and so on. Exponential functions, which is the domain is the entire real line, those are continuous everywhere. Logarithmic functions, the domain is the strictly positive numbers, those are continuous in that domain. So all the kind of functions that we see every day, in day-to-day, I guess I shouldn't say day-to-day life, but day-to-day mathematics for sure, and maybe applications if you're doing engineering or physics, all of those functions are going to be continuous provided you stay within inside the domain. Other functions exist, but those are a little more complicated. You have to take a little bit more care to write them out. But a lot of the everyday functions we see are continuous. Okay, and also if we have a function that's continuous and we can find the inverse of it. So remember that to find the inverse of a function, it needs to be 1-to-1. If we can find the inverse, then the inverse will be continuous too. For instance, these appear in pairs, right? Trig functions, inverse trig, exponential, inverse exponential, which is logarithmic. Those are all pairs. Okay, so inverses of continuous functions, provided the inverse is defined, are also continuous. So now we have a lot of functions that are continuous, and we also have rules for putting together continuous functions to get more continuous functions. So let's see how we can use those ideas together. So here's a typical example. You might see, where is this function continuous? And it's a big mess with stuff we've already seen before. Okay, so where is ln plus inverse tan divided by x squared minus 4 continuous? And the idea is to break it down. So look at the individual pieces separately. So the pieces I see, so by pieces I mean pieces that appeared in the previous list, right? Functions that we tend to think of separately. So for instance, natural logarithm. We said logarithmic functions are continuous everywhere in the domain. So in particular, here the domain is 0, infinity, open-ended at both sides. So this is going to be continuous on 0, infinity. Inverse tan, the domain is the entire real line, so it's going to be continuous everywhere. And then we look at the bottom. Okay, so well, let me not go there yet. Let's use the two steps. So ln x is continuous on 0, infinity. Inverse tan is continuous on the whole real line. So if we want both of those, right, the numerator is the sum. So both of those are going to be continuous at the same time on 0, infinity, right? If I want the top to be continuous, I need both of the individual pieces to be continuous. So I need to restrict to both 0, infinity and minus infinity, infinity. Okay, if I have to be in both of those, I get the second one for free, but I need to make sure I'm in the first one, so I need to be inside 0, infinity. So both of those functions are continuous on 0, infinity, so I can then use the sum rule. I can sum two continuous functions, so the numerator is going to be continuous on 0, infinity. Okay, and then we look at the denominator. Now I can finally get to it. So that's x squared minus 4. It's just a polynomial. The domain is everything. It's going to be continuous everywhere. But if I want to use the quotient rule, right, the rule about combining continuous functions with quotients, then I'm going to have to make sure the bottom is non-zero at the points where I'm taking the limit, or the points where I'm checking continuity. Okay, so x squared minus 4 is 0 at plus or minus 2, and it's non-zero at everywhere else. So now if I want to say, I have a continuous top and I have a continuous bottom, so the fraction is continuous. Remember, we said we can do that provided the bottom is non-zero. Okay, so if we want to consider this function overall, I need the top to be continuous, so I need to be in 0, infinity. I want the bottom to be continuous, which is everything, that's fine. And I also need the bottom to be non-zero, so I have to throw away plus or minus 2. Okay, so we land with 0, infinity, take away 2, which is going to give us 0, 2, and 2, infinity. So basically the idea is figure out where each of the building blocks are continuous. Then we're going to want them all to be continuous at the same time. So we have to choose the most restrictive possible. And then we're going to have to check the bottom is non-zero. Okay, so those are the different steps. Okay, so now moving on to composition. So remember the composition of two functions is this thing f composition g at x. It's defined by f of g of x. So first x gets mapped to g of x, and then that gets mapped to f of g of x, provided the right side makes sense. Okay. So how do limits and composition work? So here is the good news. So suppose the limit of the inside exists and the function is continuous at that limit point. Then we can bring the limit inside. Okay, so if the limit of the inside exists and the outside function is continuous at that point, then we can bring the limit inside. So the limit of f of g of x is f of the limit of g of x. And quite often you'll have functions which are continuous everywhere, and then if they're continuous everywhere, then things work out nicely. You can just bring the limit inside. But there is something to check, right? If they're not continuous everywhere, you have to check the limit of the inside exists, and you have to check that f is continuous at that point. Okay, so let's see in a very simple example. Let's try to find the limit as x tends to 1 of the natural logarithm of 5 minus x squared divided by 1 plus x. And if I think about, instead of the limit of the composition, if I were to just think about the limit of the inside, so the limit of 5 minus x squared divided by 1 plus x, that's a rational function. 1 is in the domain. We can find the limit by substitution. It's just 4 over 2, which is 2. And now the outside function, natural logarithm, is continuous on the entire positive real line. In particular, it's continuous at 2. So because it's continuous at the limit point of the inside, we can bring the limit inside, right? So the limit of the composition is going to be ln of the limit of the inside. It becomes ln of 2. So this is really useful if we have complicated limits with composition functions. We can bring the limit inside provided the outside function is continuous at the right point, which is true for a lot of functions, right? All the functions we saw in the garden are continuous. Okay, and that's basically what I said. Okay, but let me emphasize that we really need to check the condition that the outside function is continuous at the limit of the inside. So here is a simple example showing why we need to do that. And why do I always say this example of what is the downside? Why do we need this condition? Well, if we didn't need that condition, we could just upgrade our result for free by getting rid of it, right? So whenever you have a condition in a math result, it makes sense to think, is that condition really necessary? Otherwise, you could just have a better condition and never worry about it again. So why is it really necessary? So let's suppose that f of x is equal to 1 if x is non-zero, and f of 0 equals 0. So that's going to be our outside function. It's a little bit complicated definition, but we can understand it, right? It's f of 0 is 0, and f is 1 everywhere else. And g of x is just going to be the identity. So nothing complicated, very simple function. And let's suppose we want to find the limit as x tends to 0 of f of g of x. Okay. Well, g of x is just x, so I can replace the g of x by just x. So that's the same thing as the limit as x tends to 0 of f of x. And now I forget everything from this video, and I'm just trying to find the limit of f of x as x tends to 0. And remember, with x tends to 0, we're not caring at all what happens at 0, only what happens when we're close to 0. Okay, if we're not at 0, then the value of the function is 1. So the only thing that it can approach is 1. So here the limit is 1. And then if I want to compute the f of the limit, so if I look at f of the limit as x tends to 0 of g of x, then g of x is just x. So that's f of the limit of x. The limit of x as x tends to 0 is just 0 itself, right? X is a polynomial. If you substitute, you get 0. Or you can just think, x approaches 0 as x approaches 0. So we get f of 0, and okay, f of 0 was 0. And these are two different numbers. So what we managed to show is that the limit of the outside, the limit of the composition was not f of the limit. So we could not bring the limit inside the outside function in this case, right? We could not bring the limit inside. So this is basically saying the result that we claimed before is not true in this context. So why is that? Well, as you can guess, the outside function is not continuous. So we really need to check that condition that the outside is not continuous. Okay, so we looked at composing functions and limits and bringing the limit inside. And there we said that the outside function should be continuous. What about if we have two continuous functions? Can we compose them? Okay, so if the inside function is continuous at a and the outside function is continuous at g of a, then the composition is continuous at a. So f or g is continuous at a. And why are f and g supposed to be continuous at different points? Well, remember that g, if we start with a, then f or g of a is f of g of a. So we're applying f to g of a, so it's natural for f to be continuous at g of a. Okay, but don't worry about that too much. A lot of the functions you're dealing with, they're going to be continuous at most points, except for maybe one or two bad points. So they're going to be continuous at most points. So you're going to have these conditions for provided you're dealing with nice functions. So if you have two continuous functions, then the composition should be continuous. Okay, and why, I'm a pure mathematician. Why is it true? If I want to take the limit of the composition, that's the limit of f of g of x. Okay, if f is continuous, I can bring the limit inside. If g is continuous, the limit of g is g of a. So somehow I end up with f of g of a. Okay, but that was exactly my composition at a. So that shows this is continuous. Okay, so here are some examples. For instance, we know that all polynomials are continuous in the domain. We know that sine is continuous everywhere in the domain. We can compose them. We get that the sine of, say, x squared plus 5x plus 4 is continuous, right? It's a composition of continuous functions. And the same story with e to the x, right? Exponential functions are continuous in the domain, which is everywhere. We can take, cosine is continuous. We can compose them. We get cosine of e to the x is continuous. Then we have two continuous functions. We can add them. They're continuous. And here I wrote 0 infinity, but actually everything is continuous everywhere. So this could also be negative infinity up to infinity. Okay, now if we look at ln of sine x, for instance, sine is continuous everywhere. But if I want to compose them, I have to remember where is the composition defined, right? If I want to deal with natural logarithm is only defined if the input is strictly positive. So if I want to compose these functions, I need the inside to be strictly positive. So I need sine x to be strictly positive. Okay, an interval for that could be 0 to pi. Okay, so if I take a between 0 and pi, sine is continuous. Sine of a is going to be strictly positive, so ln is going to be continuous. Hence, ln of sine x is going to be continuous. Okay, so the takeaways from today were a lot of the functions that we see in everyday calculus, like polynomials, rational functions, trig, inverse trig, exponential, logarithmic, all of those functions are continuous. Once we have continuous functions, we can combine them to get more continuous functions. But we have to be careful, right? Not every function is continuous. There are some that are even easy to write down that are not continuous. So we have to be a little careful, but more or less, we start from a few continuous functions and we can generate way more. Okay, thanks everyone. See you next time.